Okay, so the first presentation is going to be leveraging an actual relational structure for integrated planning, learning and planning. Okay, Wang and Felipe Trevizan, so we're going to get started. Okay, and here we go. Okay, thank you.
Thanks, Hector. So this is joint work of my former student Riot and couldn't make it here today. So the motivation for this work is most of the learning approach that we have for planning, it's planning first. So what I mean by that is we look at our pipeline, our planning pipeline, and we ask, what can I replace with machine learning, right? So for instance, if we're doing a heuristic search, we look, well, can I learn a heuristic, right? So if you're doing problem transformations, can I learn a problem transformation, right? And the whole idea of this work is to design both the planning and the ML parts together, instead of just asking what can ML do for us. Let's try to work together and see if we can achieve something better, right? So that's the motivation. So in this work, we're going to be focusing on learning a heuristic, right? And in learning for planning, we have a fair amount of work on that. And you can learn directly a heuristic, or what we have shown in our group is that you can learn a global ranking, something similar. And we also have shown that you can search, so you can learn a proxy for search effort. But what all of these works have in common is that we are learning a function from a state to the reals. And then you just plug that in your GBFS, and that's it, right? So in this work, we're going to do something different. We're going to learn a heuristic from a set of states, right? So 2 to the S to the reals. And then we're going to design a planner that's going to do iterative refinement over this set of states. So we're going to start with a very large set of states, and as we expand nodes, we're going to shrink them and so on. Okay? So I guess the main question now is, why do we want to learn why we want to do this search on a set of states or learn a heuristic for a set of states? The first one, I guess, is quite obvious. We can ignore a set of bad states, right? So if I have a very large set of states and I have a very high heuristic value, it's going to go to the end of my queue. I'm not going to have to bother with that, so I put in a lot of things with just one single query to my heuristic. The other interesting thing here is that for machine learning methods that we have been using a lot for learning heuristics, they do not distinguish between a single state and a set of states. They're all based on graphs, right? So you give me some planning object, I will represent it as a graph, and then I use that graph to learn something. Think about a GNN or a WL kernel, right? So then these ML methods, they don't care about what is inside of your graph. So then we can exploit that to make predictions over a set of states. So it should be an easy thing to do. So then what we're going to do here, we're going to represent states in our search as a pair that's our regular state in a partially grounded action. Then we need to design a planner that's going to do the search on that space. And then, as I said, we need to learn a heuristic for it, right? So that's going to be the outline for the rest of my talk. I'm going to show how we did each one of these 3 steps. I'm going to start by just defining what is a partial action. So a partial action is just an action schema with some of the objects already instantiated. It can have no objects instantiated, can have all objects instantiated, and anywhere in between. We also need to have this special, so just in terms of notation, A here is going to be my action schema, and then every single object that I already instantiated, I'm going to show. If it's not instantiated, just have the underscore there saying, I don't know what to place there yet, okay? We need a special token here that's going to be known, just to say, well, I haven't made a decision yet on terms of action schemas, but also to be able to represent the singleton set, right? A set of just one state inside is going to be that state in known. I need just one more definition here. It's just what is when this partial action is going to be applicable. Pretty straightforward. These partial actions represent a set of actions. In that set, if there is one applicable action in that particular state, I'll say that partial action is applicable in that state, right? And known will match with all the actions, right? So I state in known, if that state has any applicable action, I would say that then I can expand that. All right? So now that I define what a partial action, we can look at the search space that we call partial space search. So we're going to start here with our initial state and known. Remember, this is how we represent a singleton set, a set of a single state. And then we just expand that, we start with the action schema. So in this case, we have 3 different action schemas, one with 2 arguments, one with no argument. So one with 1 argument, one with no argument. And then we just keep refining it, right? And then instantiate the first one and so on, okay? Fairly straightforward. So now the first advantage, that's the planning advantage. So what we can do here now with this, we can have that early pruning that I said in the beginning of the talk. If I can find a particular action schema that is really bad for that state, I can prune all of that in a single movement, right? So for instance here, if I can predict that this action schema for all the objects, in the case, let's suppose there's any objects, is a bad action, then instead of having to instantiate these any states, go there and query the heuristic n times, I can just query once and prune it all there, right? So that's actually already a win for machine learning. So these machine learning-based heuristics, they tend to be more expensive than classical heuristics. So just avoiding having to evaluate all of this is already a win for the machine learning heuristics, okay? But the whole part here hinges on how can we find a heuristic for this, right? So in the paper, we show how we can adapt classical heuristics. They don't perform all that good. So what we're gonna do here, we're gonna learn a heuristic for this set of states. So the way we're gonna do it, as I mentioned before, we're gonna encode this set of states in a graph, and then we're gonna learn from that graph what is the target that we want. It's going to be a heuristic or a rank. So in particular, we're going to use WL kernels, something that we have done a lot in our group. We could have used GNNs or any graph-based method. But the key insight here, as I said at the beginning of the talk, as long as the object that you want to learn to map to something, you can represent as a graph, all these methods can apply straight away, right? So it could be something else instead of a set of states. I'm going to show we define in the paper 2 different graphs, all of them based on our previous work of IOGs. So the name of the graphs are not that important. They're going to be color-coded for the rest of the talk. But just here, what we're going to have actions appearing on this graph. That's why we call it direct embedding. On the second one, the blue one, we're not going to represent action directly. We're going to represent the effects of the actions. So the first graph, this graph that we do the direct embedding. So we're going to get this previous graph that we have, the IOG, right, that we have here propositions, and we have objects, and we just connect them together based on the arguments in which that objects appear. And we're going to just add actions now, right? So the orange nodes are the new things that we are adding to this graph. So then if we look here at this blocks word state where we have 3 blocks, A and C on the table, we are holding B. Now, if we have this partial action of stack B and you don't know where you're going to put, you just put your actions there, attach it to the, connect to the objects, and then to their effects, right? Very straightforward. So the second graph, what we're going to do instead, we're going to remove the actions, and we're going to look at the effect of the actions, right? So now we have to reason a little bit more about this. So what we're going to have now, you can see here that there is no actions being mentioned. We need to look at what are the effects that always going to happen, right? So if I'm looking at this partial action stack, so I'm going to put the block that I'm holding on top of something, no matter what that something is, my arm is going to be empty, right? So then I already put the effect there, right? So that is an always going to happen effect. On the other hand, there's some effects that might happen, might not happen. These are the optionally add effects. It's going to be this green and the blue, right? So I might put B on top of A, so that might happen, or I might put B on top of C, right? So then they have their own color. And similarly, we have these optional deletes, things that might be deleted or not, depending on what action here is going to be selected on this set of actions, right? In this case, it's going to be either clear A or clear B. That's the optional delete, okay? I guess the whole point here is just to show that as long as you can represent these things in a graph, all these machine learning algorithms, they don't care, right? So they're just processing the graph. They don't care about the semantic of them, okay? All right, so now it comes to the second advantage, right? So the machine learn advantage. I said before that just the fact we are not querying all the time, it's already a win. But now, so there is another advantage. is that we get a more granular data to be able to learn. So if we look at optimal plans, that's what we use for learning. That will be the solid arrows here, right? So here if you give me 3 states, I have just a single action. While in this partial search space, I have several actions here, right? So I generated more data for the same optimal plan in order to learn. So that will help us to make sure that whatever we are learning, we can recover from some inaccuracies there. But perhaps the more important part is this ratio of optimal decisions to suboptimal decisions, right? So we always arbitrarily break ties. So if we look here to the right, we have one optimal action and a lot of suboptimal actions, while on the other hand here, on every single decision, I still have one optimal one, but the branching factor of suboptimals is much smaller. So it's easier to find that needle in the haystack because the haystack's much smaller. So that, as I'll try to convince you in the experiments, that is actually quite helpful for machine learning. Okay, so then in terms of experiments, so what we're going to do, we're going to compare against Llama, our previous work on learning using WL. And we're also going to compare against PowerLifter because we're going to have these high branching factor domains. I'm going to show here both results using regular GBFS in our partial space search in our 2 graphs. All right, so let's see the first set of experiments. So here's the IPC 23, the learning track. So everything here is color-coded. So the main takeaway here is if we look on the orange column here, these 2 columns, we are just using regular GBFS. So we train a heuristic on that partial state. So it's a heuristic that can answer queries regarding set of states, but also the singleton set. But during planning, we use it as a regular heuristic. We're just querying for a singleton set. And that was enough to improve upon the previous work that WL used. In particular, this column here that we'll use in the orange with red, these graphs for a singleton state is literally the same graph. They are literally the same graph. The only difference there, it was the extra data that was used to learn that iterative refinement of doing one step at a time on the grounding of the action schema. And what we can see here also is that the other heuristic here, using the blue graph, they're not literally the same graph, but it's very, very similar, also outperform Goose, right? So that is this intuition that the extra data that we were able to extract from the optimal plans is helping, right? The same data set there, nothing very special, same training methods, same planner. But now if we look here at the purple, that's when we use GBFS on our partial space search. We can see that we have a similar performance, but we are underperforming a little bit. And part of it, there is a fair amount of domains there that don't have an insane branching factor. So for this reason, we also look into the high branching factor domains, and that's why we have PowerLifter here. And what we can see now, the partial state search really pays off, right? So here we have blocks word large, is problems with thousands of blocks where just very few of them are relevant. We have transport with very large graphs and different densities. And we have here warehouse that is a similar problem to blocks word, but with an even larger branching factor. There's a quadratic branching factor there. We can see that the partial space search really shines there and outperforms PowerLifter. And now if we bring all the results together, we can see that, yes, partial search with our graphs overall has the largest coverage. So we were able to kind of have a not so much compromise here, right? So we got both improvement on the IPC and the high branching factor. We didn't have to compromise one for the other, okay? So just to wrap up, I guess the main message here is using the set of states through these partial actions provided this better integration between planning and learning, right? So we were able to learn a more informed heuristic, right? Even though we didn't use it in the partial state search, just using regular GBFS, they perform a little bit better. And also, this new space search, this partial search space, performed really, really well on the high branching factor domains. Thank you.
Okay, thank you. Okay, time for questions. Carlos.
Yeah, so I understood the part of like how you are able like to encode this like partial state to obtain like a heuristic value like for the whole like set of like random states. But when you do the partial states search, I didn't quite understand like how do you obtain like this partial state and you order that like with a heuristic. So do you like start like choosing the action schema, then you choose like the first object, the second object, like to prove early with this heuristic?
Exactly, right? So let's say here we start with the initial state in known. So then we look into the action schemas. They have at least one applicable action in the initial stage. And then we schedule them based on the heuristic for these partial states, right? So this represents a set of states, right? So this in particular will be a single state. And we query the heuristic over the set of states. And it's just your GBFS. But the query now happen on this pair, right? And this pair can represent a set of states.
For example, in that example, you would say you query the heuristic on that, like those three partial like sections, and then, for example, you say like A1 is better than A2 and A3. Then I say I will choose A1, and then I choose like the first object. Then I
Exactly. Yeah, we are doing that from left to right, right? So then I will pick, let's say the A1 has the smallest heuristic, so then I will remove that from my queue, and then I'm going to expand, and then I expand that by grounding the first argument. I see from the set of applicable actions on that particular state that has that action schema, I see all the first objects that is in the grounding.
Oh, but what do you do? So you rank them, but what do you do? Imagine like A1 is the best one. What do you do with A2 and A3? Do you put that in your queue?
Oh, that's still in the queue, right? It's just regular GBFS.
Because it can be that for the set of state of O1, you see, oh, this is a really good state, but then you ground them, and you see that actually, like, because you have some errors, it wasn't those. So would you go back to A2?
Could really be the case. Could be the case that all these nodes end up being behind that. Yeah.
Great. So let's pass the mic. Yes.
Cool. Sorry, just a quick one. I assume that the kind of target, when you're learning the heuristic for a set of states, I assume it's the minimum of the, like, what value is what's the kind of target value?
So that's a very good question. We tried to learn a heuristic value, and that didn't perform very well because you have this ambiguity. So we end up learning a rank, because the rank is very easy, right? So you're just saying, okay, I prefer this over that, and so on.
And so, a question for me. So, if this heuristic is coming from neural networks, so it is issues about overhead, right? So, in a sense, they're more expensive to compute than with planets. So in a sense, the comparison is very good, even though it takes more time to compute the heuristic values, right?
Yes. So in the extended version of the paper, we show that we do a lot less querying of the heuristics, but we do more expansions, right? So then we kind of move a little bit of the overhead instead of being on the ML side of it, the embeddings of these graphs towards the expanding nodes and reordering the queues, right? So we didn't have the time, but I guess now we have a good way of having larger embeddings with L4. So I think this will really pay off there because we are not having to embed that often.
Okay, great. Okay, so let's thank the speaker. So.